My name is Vipul. I'm a software engineering manager in the Azure Service Fabric team. And today we're going to talk about actors. So here is the agenda for my talk. So we're going to briefly touch upon the Azure Service Fabric platform. We'll then go and build some reliable actors. We'll then go take a deep dive into the reliable actor API features. This is where we will spend bulk of the time. We will then look at how do we scale. So once we have built an application, how do we scale that application? And then finally, how do we manage and diagnose an actor-based application? Right? So Service Fabric is a platform for building distributed hyperscale microservices. You have seen probably Mark Russ talk about it at the build keynote, as well as today Mark. There have been a lot of talk about how to build applications in a microservices way. This is the platform on which you would want to build the microservices. So within Microsoft, we had many box products like SQL, Intune, all of those. When they wanted to move to cloud, they were looking for a platform that allowed them to solve hard distributed systems problem in a fundamental way. And Service Fabric was born from those needs. So Service Fabric provides a lot of capabilities that are listed here, basically high availability, failover, replication, orchestrations. You probably saw Matt's talk today about orchestration, application lifecycle management. Today, we are giving you an SDK that you download. You can develop this microservices-based application on your local one-box cluster. The same applications that you develop can be deployed in Azure when we provide a hosted offering to host microservices. And so that's the Azure part that's there. You can also host these applications in a private cloud, as well as you can host this application into third-party hosted cloud. We are going to make this technology available as part of the Windows Server 2016. So you can just stand up a cluster on-prem and actually deploy the same application. Your application does not change at all. Also, we are porting this application, this platform to Linux. So today you can develop applications using C#, C++ APIs. We are also looking at providing more language bindings like Java and JavaScript. Right. So this platform is been in production for more than 5 years under various Microsoft services. So core Azure infrastructure services such as the resource provider, if you know about them, the compute resource provider, network resource provider, storage resource provider, the one where you define the template and you say, well, I need these resources. Those services that are providing you those resources are actually running on top of our platform. SQL Azure, which is managing 1.4 million databases, is running on top of this platform. Cortana is running on top of this platform. And we're giving you the exact same bit. It's not a different fork of the bits. It's the same exact bits that you can actually develop your microservices in. So once you've decided that you want to build microservices on top of Service Fabric, well, what are the ways in which you can build the application? So you can build applications using actor APIs, or you can build application using services APIs. We talked about services API in a programming model talk that we did 2 days ago. I encourage you to go and watch the recording of that to get the details. Today we are just going to focus on reliable actor APIs. So what the heck is an actor? Like people keep talking about, oh, there is an actor programming model, here is an actor. What is an actor? So the idea originated sometime in the early 70s when there were parallel computing, distributed system was kind of the thing that people were looking to scale their workloads. Right? So at that point in time, in order to make sense out of the distributed computing and make it really easy to program against those large mainframes, multiple ones of them, the actor concept was born. So what it tells you that, in a nutshell, think of it as a processor which has a single thread. There are no multi-core, there are no multi-threading. It's a processor with a single thread. It has its own memory, which is where it keeps its state. and it has basically the code that executes some logic. And in order to talk to another actor, it can only do so by sending a messages. There is no shared memory. There is nothing of that sort. You can only send asynchronous messages to other processors or other actors. So this makes it really easy to write your code. First, it's a single-threaded execution, and hence you don't have to worry about concurrency. You don't have to worry about shared access, lots of synchronization logic, and you can say, hey, and you can also achieve parallelism by running multiple ones of them concurrently, because all of them are independent, right? So that's what is an actor. Think of it as basically a processor with a single thread, memory, code, and a way to communicate to other actors, right? So reliable actor API, you can build reliable stateless and stateful microservices with a virtual actor programming model. So the word virtual here is different from other actor programming model. The virtual means that the actor always exists. You never go and create an actor explicitly. They always exist. You can address them, you can talk to them, and as needed, the system will spin up those actors, will activate those actors. And if they are not needed, those actors will die down. And so there is automatic memory management in the system, right? You can harness the full power of the Service Fabric platform. So when you write a stateful actors, you're basically using the reliable replicated storage that the platform provides. You get failover, you get placement and orchestration, you get zero downtime upgrade. All of the investment that as a Microsoft we are making in terms of making this platform developer friendly, you will get all of those benefits as well as all of the security and diagnostics. So you can say, hey, I want to run a particular actor as a network service, or I want to run this particular actor as this particular domain user or a group MSA user. You can do all of those things, which you cannot do with other frameworks, right? And obviously, this is suitable for application where you get this multiple independent unit of state and compute, such as game and IoT. The other difference is that you can build microservices that are actor-based, as well as you can build microservices that are like web apps or other things. So you basically get the best of both worlds. You can have some of your services where it is very natural for you to break down this state into independent unit, you create actors. Where it is not and you want to actually have a transactionally consistent operation done across a bunch of state, well then you use reliable collection APIs. If you have a web application in your web service in your application, great, you use a stateless service APIs with your web API, right? So it allows you to build all of these together on top of this platform, which is different from if you were to get just an actor programming model, right? So what does a cluster look like with the reliable actor? So you start with a bunch of machines, and the runtime or the service fabric is running on them. It stitches these machines into what we call a cluster. The cluster has a bunch of nodes. Typically, one node is one machine, but on a scale minimized environment, like on a dev box, you can run multiple nodes on the same box. You can start as small as, let's say, 3 nodes, and you can expand as large as thousands of nodes. Some of the internal customers have clusters that have thousands of nodes in those clusters. So once you have created the cluster, you kind of start building microservices, applications built with microservices, and then start deploying them in the cluster. You tell the cluster, hey, I have this 2 application I want to deploy. It will take those microservices and then place it appropriately within the cluster. This is quite different from, let's say today, if you were building on web and worker role, the PaaS V1 as we call it, your VM is your application. You start thinking in terms of VMs, right? So you say, hey, I need 5 web roles and I need 10 worker roles. And whenever you try to update, you're basically updating the entire VM. And when you push out your application upgrade, it takes 15 minutes because the VM has to go down, new bits has to be copied, and then the VM needs to spin back up. Plus, there is no health monitoring, and so if you deployed wrong bits, for example, basically within an hour you will have a cluster of all dead nodes, right? And your application would go down. So with Service Fabric, you start thinking in the microservices way, and you can say that I can update them independently of each other. So I can update this app 1 independently of app 2. I start with a well-defined contract between those microservices, and they can just coexist in the same cluster at a much higher density. And if you watch Matt's talk, you can also define lots of interesting things. So you can say that, oh, I want the purple services to exist only on X set of node. I want this services to exist only on this node. You can define matrix and you can do load balancing. So now, obviously, with Service Fabric, you get automatic failover. So if a node were to fail, Service Fabric knows what microservices are actually deployed on that node and then basically replaces them. So a different graphics that I'm showing here, which is a bit different from what you have seen in the other talk. So when I show a hexagon that has a man in it, that's basically an actor-based microservice. The one without is a microservice, which is a reliable services API or any other microservices that you have created, right? So how do we create a reliable actor? Now, if you look at the definition that I mentioned, which is of an actor, there is a single-threaded execution, there is a independent state, and there is a logic that operates on that state, and then you communicate to those actors using messages. Now, this looks very familiar to an OO programming, right? I have an encapsulated state in my class, and I have methods that operate on that class. The only difference is that, well, no more than a method is executing at the same time, or not more than a single thread is executing inside those methods at the same time. So in order to create a reliable actor, you start by defining an interface. So this is your well-defined communication interface. This is how you are going to communicate to that actor, right? So you start with an actor interface deriving from iActor. You implement that actor interface, and then you register your implementation with Service Fabric. So this way, Service Fabric knows that how do I actually activate this actor when it is needed? How do I fail over it when it is needed, and so on and so forth, right? So pretty simple. Now, once you have created the actor, registered it with the runtime, you say, well, I want to connect to this actor. How am I going to connect to that actor? Well, so in order to connect to anything in the cluster, you need to identify it. You need to say, how am I going to talk to it, right? What's the identity? So an identity of an actor can be a string, can be a long, or can be a GUID. Remember, these are virtual actors. They always exist. So you can come up with a name that makes sense to you, and you can say, hey, I'm going to talk to that actor. You can say, hey, the actor called counter1 is going to store counters for a particular service, and that's where you will go to find out the value of that counter, right? Now, this actor don't exist on their own. Once you build the actor, you put it in microservices, right? So those microservices have name, in this case, Hello World actor service. And you put this microservices inside an application, or you instantiate the microservices in a context of what we call an application. So that application has a name, right? So the full identity of the actor is your application name, your service name, and then the actor ID. So how do you connect to it? So you connect to it by creating an actor proxy. You say the type of the contract that you want to connect, and then you specify the actor ID, you specify application name, you specify the service name, and then once you get the proxy, you just talk to it normally, right? Now, there may be more services inside that application, right? So you may have some web service, you may have some reliable services-based microservices inside that application. You may have other actor services inside that application. So you say, well, I'm already operating in the context of an application. Doesn't the runtime know which application I'm part of? And so why do I need to specify this application name? Well, you don't. So if you are outside of the application context, then you will specify the application name in order to create the proxy. If you are inside, you don't. And most of the time you will have one type of actor or one actor that is implementing the IO hello world. So if that's the case, you also don't need to provide the service name. We can infer the service name from your actor contract itself, right? So most of the time when you are contacting your actor within from the context of an application, all you specify is the actor ID, and then you talk to that actor. Make sense? Okay, let's go ahead and look at an example stateless actor. Okay, 7. Okay, so here is a counter actor. It's implementing a counter actor interface. So this is my actor interface that I have defined. It has a set, get, and a compare and exchange method. I've implemented that using a member variable and then a simple methods, right? I've registered that actor with the runtime. So let's go ahead and deploy this solution in the cluster. And then on the client side, I'm connecting to that actor by specifying the counter one as an actor ID and an application name. This actor is actually, so this client is running outside the context of an application. It's a console application. It's running outside the context of an application, and hence I'm specifying the application name. Right? So let's see if the cluster is, if the application is deployed. So this is a 9-node cluster that is running on this local box. And this is what we call a Service Fabric Explorer. It's a tool that ships with the SDK. It allows you to monitor, visualize, and manage the cluster. So I'm going to refresh. So here is the counter actor application. This is the application in which there is a microservice, which is the counter actor service, and the actor are instantiated in the context of this service. This is running on node 3. I'm going to go and start the client. So the client is simply using compare and exchange method in order to connect to it and then increment the counter, right? So I wanted to show one more thing because some of you have seen this demo. So I said, well, maybe let me try to restart the node in a different way, right? So we know that this partition has one instance of this service and it's running on node 3. Let's actually look at node 3. And here is the code that's running on node 3. This is the counter actor that we have. So I'll go back here, put this to refresh. And then what I'm going to do is that I'm actually going to kill node 3. And the way I'm going to do that is to basically show you what represents a node. So there is a process which is called fabric exe, which represents the node. So in this case, let me find a fabric exe that's a node 3. So this is the fabric exe, which is the one that is the service fabric node. So I'm going to go ahead and delete or kill the exe. That process dies. You'll see that the actor will disconnect and say, hey, that's not available. Service fabric will take a failover action, restart the actor microservice on a different node, and then you connect. The actor proxy will transparently reconnect. Obviously, we lost the state because we were storing the value of the counter in a member variable, and we start the process on a different node. It's going to initialize itself to 0 and start from there. So we made the code reliable, but we haven't made the state reliable, right? So let's go ahead and look at how do we make the state reliable. So I'm going to switch back to the presentation. So in order to make the state reliable, you need to be, the system needs to be able to serialize that state and then send it across to be able to store it somewhere, right? So you basically define an actor state which is either a bracket serializable or a data contract serializable. Then you derive the actor rather than deriving from actor, you derive it from actor of T state. This will give you a state property that you can use in your methods. Now you say, well, great. So how is the property state is making this, this state reliable, right? So in order to understand that, let's look at the life cycle of an actor, what happens to an actor, how it comes to life, right? So here I have shown an actor based microservice. The gray represents that there is no actor active in this microservice. So when we wrote the code and we registered the service with the runtime, so we registered the actor with the runtime. There is actually no actor that is currently active until the client connects and say, hey, I want to connect to a particular actor. So this service says, hey, I support this type of actor, but there is no actor active in the system at that point in time. The other two node basically represents the replica of a stateful service. So stateful services will have a primary and a second and secondaries, and you can define how many primaries and secondaries you want. So an actor method call arrives on, let's say, counter 1, which says I want to set a value to 10. The system says, well, counter 1 actor is not present, so I'm going to instantiate it. So it will instantiate the actor. The black represents basically a .NET object that got created inside the process. Then we load the state if it was already present. If the state was not present, we will not load the state. So we'll load the state from the primary. We then call what is onActivate async method. So in your actor, you can override a method called onActivate async. This is where you can perform initialization. So for example, if your actor state does not have a public constructor, then it is no way for runtime to be able to instantiate that. So let's say you can check in your onActivate method, hey, is the state null? If it is null, I'll initialize it to some value. Or you may perform any other initialization that you may want, right? Once the onActivate returns, the system thinks that, well, maybe you have manipulated the state even in onActivate. So when a particular method returns, that's when we go ahead and replicate the state. We take that property, we serialize it, and then we replicate. Once that is done, we then call the actual method. So we dispatch the call. In the method, you may do the modification, and the set value async returns. At the same time, now we replicate the state again, and then we return the response to the client. So at any point in time, if there is a failure, the actor gets activated, and then we load the consistent state from the primary again. At some point in time, there are no more method calls on this actor. So system says, well, I'm going to deactivate the actor because it is taking up space in the memory. So it deactivates the actor. And that happens after an idle interval. And you can control this idle interval through an actor GC attribute on any actor, actors of any type. So you can say that this particular actor, counter actor, I need it to be alive for 10 seconds. If after 10 seconds no calls come in, we'll deactivate it. Some other actor, maybe a stock ticker, says, hey, I want this to be active for 24 hours, or I want this to be active for 12 hours, and after that, if no call arrives, deactivate that actor. So you can do that. Once the actor is deactivated, we make a call called onDeactivate async. So this allows you to release any resources that you might have acquired on activate. You might be able to do some more cleanup in the onDeactivate async call. After a certain point in time, after onDeactivate is called, and if there is a memory pressure, the actor gets GC'd by CLR. Right? So now you are back to the state where you started with. There is no actor in that process. So if you, let's say, you get lots of call and lots of actor gets activated in the process, if they are not needed, the system will deactivate them. Their memory will get garbage collected. And that's how you can have large number of actors operating concurrently, and then as they come in, they'll go, and then the system will continue to manage the memory for you. So let's go ahead and look at, so you say, well, this is great. So in the previous slide, we saw that the state got replicated and saved after every method call. Now, you can say, well, I want to actually control when the state is saved because there is a method which says get value, and I know I'm not doing any modification in the state in that get value. So why are you paying the cost of replication or replicating the state when there are no modification? So what you can do is that you can actually mark the method as read-only. You can mark that either in the interface or you can mark that in the implementation. Because sometimes once you define an interface, it may not be clear whether the implementation will actually make the state immutable or not. And so you can do that even at the implementation time. You can also save the state on demand. So let's say you are performing a lot of complex operation in your method. At some point in time, you say, well, I've done all of these operations. I've sent some messages to other places. I want to make sure that I want to take a checkpoint of my state at this point in time so that when it starts again, it will have this state. So you can call save state async at any point in time in your actor method, and we will do the same replication magic that we're doing when your method is returned, right? You can also control the durability and reliability of the state. So by default, when you get a stateful actor, the state is durable. So when we replicate it to those replicas that I showed, it will be saved on the disk by default. But you may say that, well, for some of the application, that's really not necessary. If I'm doing a cache kind of an application, or it may be a shopping cart where the reliability of it being replicated to end replica is good enough for me because I will not lose the data unless all of those replicas simultaneously go down. If one replica were to go down, we will elect new primary, even though the state is in memory. Another replica will spin up, and then it will copy the data back from the primary. So you still will not lose the state. You will only lose the state, in-memory state, if all the replica were to die simultaneously, right? So that may be good for certain application. For some game application, this is perfectly fine because you are not storing the state to disk, your throughput is much higher. There is no I/O involved. You're just basically replicating the traffic and storing it in memory. So for some application, this may be useful. Right? You can also control the replication factor. So you can say, hey, I want actually 3 replicas, or I want 5 replicas, or I want a single replica. In some cases, you say, well, I actually want only 1 copy of the actor. I don't want multiple copy, but I want that copy to be the copy. I want 1 leader in the system. I don't want multiple guys, right? So you can actually create a volatile state, use a volatile actor state provider, and then use a replication factor of 1, which means that there is always going to be 1 primary in the system. Now, we haven't mentioned it in any other talk, but it was kind of implied that we guarantee that at no point there are going to be more than 1 primary in the system. If that happens, that's a complete violation of consistency, and that's not allowed in the system. You can also customize where the state is saved. So this is where you can say that, well, some framework allow me to say I have an in-memory state, but I want to store the state actually in a backend store, a SQL. I like the programming model, I like the failover, but I'm not ready to store the data into the reliable store that you provide. Well, you can do that. So you can actually write a state provider, and we have an interface for you to write the state provider, and then slap an attribute on your actor and say, hey, use this state provider, such as an XStore state provider or a SQL state provider, right? And then we will make the appropriate calls to your state provider when it is time to save the state or load the state. And now you have your states stored somewhere else.
Quick question. If you're saving into disk and you have quite a big state, there's obviously a penalty associated.
Correct. So this is one of the difference between the actor programming model and the reliable services programming model. If you have seen the slide where we talked about the granularity is something that you do not control in the actor programming model. The entire state gets saved. We are looking at ways of providing it, but then it's kind of going into the realm of reliable services API, where you can say that, hey, I can actually control the granularity at which you want to save. If you have designed your actor in a correct way, you typically would not end up in a situation where you are thinking, oh, I have a very large state, because by definition, actors are supposed to have a very small independent unit of state. Right? So let's go ahead and look at the reliable stateful actor. So here is a stateful actor. The only difference is that I have marked the get async as read only, and then I've derived it from a counter state, and I'm using that inside this method. Now, I'll do a different thing here. I'll press F5 at this point in time. So this will deploy, and it will allow me to debug and see what's going on. So a diagnostic viewer should pop up, and we can look at that and see what are the things happening that we just talked about in terms of the life cycle of the actor. I'll also start the client so that we can look at some of the methods. Pause this. So you'll see here is that a compare exchange is being invoked. So this one says, well, I'm invoking a compare exchange method. So compare exchange method is being invoked. We are printing the value. This is coming from the actual actor code. So if you look here inside the actor code, this messages are coming from here, which says, hey, this is a compare exchange method, and the current counter value is this, which is what is coming in the diagnostics event. So this message, as well as this message. So once the compare exchange is finished, you can see that we are starting to save the actor state, and then we finish storing the actor state. We'll talk about this waiting to acquire lock in a bit. The next method that is getting invoked is this get async method. And you can see that because for the get async method, we have a read-only attribute. Once the get async method finishes, there is no start and stop for save. We're not saving the state. So we're not replicating the state, right? So let me detach from the debugger. Make sure that the client is running again. Now, we have done the failovers of a primary, and we know that, well, we can survive the primary failover, right? So what I'm going to do this time is going to do something actually more chaotic. I'm going to restart all of the replica at the same time. So you'll see that all of these partitions will basically, all of the replicas will go offline. They will all go down at the same time. New replica gets built, and we know which replica was previously primary. So we'll ask each of the replica, hey, there is a concept of, in the replication, a logical sequence number. We'll ask which one has the highest LSN, so which one has the right data. We'll elect that guy as the primary, and then rebuild the other replicas from that. And you can see that even then we haven't lost the state. If all of the replica went down at the same time, we didn't lose the state. So I'm going to stop the auto refresh and just show you the volatile actor state provider as well. I'm going to go back to this actor and say I want to use a volatile actor state provider. So I'll redeploy the solution. Now, actually, you may see when I go into Service Fabric Explorer, you may see some red warning pop-ups. Ignore those because I'm reconnecting to the application without allowing it to get stabilized. And so there might be the health state is not propagated, and we try to make a call to say, hey, get me the health, and the health is not there. But those are fine. You'll see here that, well, in this case, it's all done. So, well, yeah, you'll see some of these active primary, yes, the health state is not propagated, and so we say, well, there is no health. In a while, they will all be fine. But yeah, so they're all fine now. So let's go ahead, start the client again. So at this time, let's first do only a failover of the primary. So I'll refresh this guy. I'll say I want to remove the replica. So I'll remove the primary. So one of the other replica becomes a secondary, and then we do not lose the state. This is fine because all three replicas have the state in memory. All three replicas didn't go down at the same time. So now we're going to do that. Go ahead, refresh this. And then we'll say, well, I want to restart the partition. I want to restart all of the replicas. So you'll see all of the replica go away. Once they are rebuilt, they don't have a data because all of the data that was there in all three replica got lost. And then when the replicas come back up, they are rebuilt. The client will reconnect. And you'll see that we don't have a data. We basically started the counter value again from 0. So this is the difference between the default durable state provider versus a volatile state provider. You can use volatile state provider in some application. It's perfectly fine to use. Okay, so I'll stop the auto refresh. And then we'll go back to the presentation. Okay, so we talked I showed you all waiting to acquire log 0 a little bit. So let's talk about it, right? So we know that for an actor, it is a turn-based concurrency. Only one thread has to be executing actor method at the same time. So how does this work? So when a method A arrives on an actor, we acquire a concurrency lock. So the blue circle says that, well, that thread or that method call has the lock. If another method arrives, whether it is method A, method B, or any other method, it will wait for its turn, and it will not be able to acquire the lock until method A finishes. Now, this is true even if method A makes an outgoing asynchronous call or makes any other IO asynchronous call. The logical execution of the method is not finished, and hence we will not release the concurrency lock. There is no interleaving. This is different from other systems where they will allow interleaving, and now you are back to adding locks and synchronization in your code. Well, that's not the point of an actor model, right? So this one, the lock is only released when method A returns. The lock is freed. The other thread will get the lock, and then the execution will continue. Right. So this is a simple turn-based concurrency. Now, as soon as you have turn-based concurrency and locking, you will wonder, well, gee, aren't there going to be deadlocks? Well, yes and no. So it is possible that you may say that so how does reentrancy work? So let's say if an actor A a call arrives at actor A, which in turn makes a call to actor B, which in turn makes call to actor C, and in that method it makes a call back to actor A. Well, the concurrency lock is already held, so are we going to now get deadlock? Well, the answer is no, because with Service Fabric, by default, we will give you a logical call context-based reentrancy. We flow the call context across. So if a method A arrives, and it comes, if there is a logical call context already present, it is used. If not, a new context has been created. And then if another method arrives, either it's the same method call or it's a different method call with a different context, it is not allowed. When the actor C makes a call back to actor A, it is allowed because it's within the same call context. Then we go back to actor C, that call finishes, actor C releases its concurrency lock, then goes back to actor B, goes back to actor A, and then the context returns. So now you basically get a logical call context-based reentrancy. Now this makes sense because actors are like object, and when I actually program or write my code in the object, they may have some cycles. And I don't want them to get deadlocked just because I'm using this single-threaded execution or turn-based concurrency, right? So you get the logical call context. Now you may say, well, I don't want this. If there are cycles in my application, those are bad. I want you to tell me if there are cycles in my application. So we also allow you to basically detect such deadlock at runtime and then come out of your execution. We will not retry those method calls. And so you can put an attribute on your actor and say, hey, this actor does not allow reentrancy. So reentrancy mode is disabled. In any case, if somebody tries to re-enter on the same logical call context, we'll say, well, the reentrancy is not allowed. Right? So reentrancy is logical based. So there is no timeout, and this is asynchronous wait. So timers and reminders. So this is, let's say that in your code, you may want to do certain things periodically. So you say, well, I create a timer, but your timer will not respect your turn-based concurrency. So when your callback fires, you are now executing, your multiple threads could be executing at the same time in your actor method calls. And hence, what we want to do is to say, hey, actually, no, that's fine. We provide a timer, so you create a timer, and then those will respect the concurrency, the turn-based concurrency. The timers do not activate the actor. So if your actor was garbage collected, it is not going to get activated by the timer. On the other hand, if you actually had a timer which fired, let's say, every 5 seconds, but your idle GC timeout was 60 seconds, your actor may never get garbage collected because your timer is continuously firing, keeping it alive. The reminders are like persistent timers. The reminders actually activate the actor if needed. So you can create a reminder and they'll activate the actor if it is needed. Reminders are also persistent in the sense that they have the exact same reliability guarantee as your state. So if you are using the default state providers, your reminders will be there even after the failover. So you can say, hey, remind me every 10 minutes. It will remind you every 10 minutes. It will activate your actor and it will make a call into your actor, whatever you specified when you created the reminders. Right? So the other feature, which is actors are just like objects, so you can pass them around. You can basically pass your actors around. You can store them in your state, and then when you read your state, we'll rehydrate the actor with the appropriate proxy so you can connect to those actors. The exceptions that you may have in your method call, they get automatically propagated as well. Now, how do we scale an actor application? So we wrote the application. How are we going to scale this application, right? So actor address space, so you know that these actors are basically independent units, right? So think of it as that there is a big 64-bit addressable range, and these actors exist, and I'm going to basically make calls onto those actors. If you had a single partition for your microservice, all of those calls for all of those actors would actually go to the same partition, to the same primary, right? So instead, you can say that, well, I'm going to create multiple partitions. So some of these calls will get routed to appropriate partition. And this is fine because actors they have independent state. There is no correlation between a state of one actor to another actor. You can create even more partitions. And then if more calls arrive, they get routed to appropriate partitions as well. The other difference is that once you create more partitions, so let's say if I had a 5-node cluster and I created 20 partitions, initially on each of the node, you can think of that there are approximately 4 primary replicas on each of those nodes. Now, as your actors become more hot, so they're taking more and more load, now one node CPU and the disk are not enough to basically take care of those 4 partitions. You can simply add more machines, and Service Fabric will scale those partitions to those machines. And so now you are basically back to having an automatic scale out. So you scale out your applications, actor application, by just partitioning your actor address space, right? So let's see how it looks like in the demo. So here I have the exact same counter actor that we have been using. This is the application manifest. We'll talk about it in a bit. This is where you specify the partition count. If you look at the previous application, my partition count is 1. Here my partition count is 10, right? So this is how you go ahead and partition the actor application. So I'll deploy this. Again, it may take time because it's deploying 10 partition. It should not take time, but when we go into Service Fabric Explorer, you might see some warnings or some errors. So here I have a counter application. These are the partitions. You can see some of them are inbuilt. Some of them are becoming ready. So this partition is inbuilt because one of the secondary is getting built. It seems all of the partitions are ready now. So here are the 10 partitions. Each one of them have actually a primary and 2 secondaries, right? So let's go back to this. Here is the program. So in this program, in addition to doing that, the counter loop, I'm actually adding more counters. So I've written a load generator. It basically creates more counter and then puts load onto the service. So let's go ahead and execute that client. So let's see if we had one counter, that one counter is going to a single partition and then the counts are getting updated. If I had more than one counter, let's say if I put 10 counters, those 10 counters in this case, gets distributed to 5 partition. If I have more counters, so let's say 100 counters, they're all getting distributed to those 10 partitions. So the operations on those actors are now getting distributed across these 10 partitions. The other benefit that you get from partitioning is that you are now dividing your application into this multiple units that can fail over independently. So if I were to go here and let's say, let me show you a different view of this system. This is what we call a cluster monitor. Many of you have seen. So I want to pick a node where there are more than 2 partitions. So let's say node 4 seems like the one which has more than 1 partitions on that node for that particular application. So what I'm going to do is to restart node 4 and see what happens here. So node view, node 4, restart. So what happened was that there were 2 partitions on this node. The other partitions are actually on the other node. So when a failover happens or an upgrade happens, you saw momentarily only those 2 partitions got affected. None of the other got affected. So even when you are doing the upgrade, like let's say you are doing a rolling upgrade, momentary interruption is basically only limited to those partitions that are being taken down in that UD. So that's another benefit that you get by doing partitioning. Right. Okay, so let's go back to the presentation. We're almost coming to end of our talk. So when we were actually building this, what we were doing were we were writing all of these code, and that code and that config was put into what we call a service package. That service package is the unit of activation and deployment. So everything that is in that service package gets deployed together and gets activated together. You can have more of those service packages inside your application package. Each one defines basically a service type. So in this case, I have a counter actor service package that defines the counter actor. I may have a web app that defines the web app service packages. What happens then is that in this cluster, you are instantiating or creating an instance of this application types. And every application instance is independent of another application instance in terms of versioning and the life cycle. You then can have more than one app type and then basically deploy those microservices. So app 1 and app 2, whether they are of the same type or whether they are of the different type, they are independent. They can be upgraded independently and versioned independently. So now let's go ahead and look at a more complex actor application where we have used timer and then go ahead and upgrade that application. So here I have an application which is, I'm going to deploy the application so we can see what's there. So while it is deploying, so in this application, it's basically a visual object that you probably have seen in some of the other demo. This visual object demo was written using the actor APIs. It has basically two packages inside of it. It has a web package, which is the one that is written using the ASP.NET or the OWIN, and another one which is written using actor. So this is another advantage. You can basically create microservices that are using different technologies along with your actor in your application. The actor is pretty straightforward. It has basically a state that is defined by this visual object, which contains its speed, its location, its color, the history color, the current rotation, and a list of bunch of other coordinates that are there on that. So if it is already deployed, we should see, yeah, so this is the actor. So each one of these flying objects are basically an actor. It has a color, the position, and the tail, which is represented by the history here, this list of coordinates, right? So all of these actors, when they activate, they register so they create a random object, then they register a timer to move that object at every 30 milliseconds, right? So every 30 milliseconds, it basically calls move object method. And then the web API is basically calling this method, which is saying that get me the state as a JSON string. And it returns the string as a JSON, state as a JSON string, which is what you see getting displayed in the web browser. So let me go ahead, actually remove the deployment of this so it's a little bit clear. So here are the visual object. I'm going to start the upgrade. Before that, let's go ahead and see this package that is there in the cluster. So in the cluster, I have deployed basically two packages of this visual object application type. You can see this is my application package. These are my two service packages that are there, and each one has a code and config. So this is the visual object, actor visual object service package. This is the web service package. And then in the case of the second version, the only thing that has changed is basically instead of basically not rotating, I'm saying rotation equals to true in the V2. So that's the only change. And now basically I have these two packages. I'm going to go ahead and start the upgrade. So as the upgrade progresses, you will see some of those objects basically start to rotate. The upgrade progresses upgrade domain by upgrade domain. So you will see the code taken down in one upgrade domain. So it was in UD1. You will see the code taken down in UD1. The replicas, the new code is basically copied onto that node, activated, and then the replicas, the primary replicas, move back to that particular UD. We'll see what it looks like here. You can see the upgrade is going on. The UD1 upgrade is in progress. So I'll let this guy do its thing. It's upgrading. In the meanwhile, I'll start also the chaos, and then we'll go back to presentation and then come back. So you'll see some of the object will start to rotate in a bit. So this object looks like is already rotating. There are some other objects that are not rotating. So they will stop momentarily as the code package is being taken down, new code package comes up. But as they come up, they don't lose their state. So they don't lose their position or their history, and then they start rotating in the new code package. So let's go back to the presentation. So we saw basically the application upgrade. So this is how you manage your application. We also saw the Visual Studio FI experience. You can put breakpoint. You can actually debug your code. We saw diagnostic event viewer. The platform also provides a deep integration with application insight and operation insights. So if you have attended one of the talk that we had yesterday, it showed basically the deeper integration. So here is one of the chart from the App Insight. It says, what are the number of actor method calls that are there? And so in this case, it says the save state, there are 43K operations or the method calls done in that particular hour. And then you can also get the calls by the actor identity. So if you have an actor 1 or actor 2, you can get all of those insights into how is your application performing, right? That brings me to end of my talk. This is the call of action. You basically download the SDK and watch the recorded talk. This is the last talk on Service Fabric. All of the talks have been recorded, and so you're welcome to watch those talks and provide us the feedback. Also, if you get chance, provide an evaluation for this session. It's very important to us. And with that, I will switch back to the monitor and let the chaos do its job while I take the questions. Thank you very much. Yes. Go ahead. Right. Correct. Correct. So that's so if you had written applications using an older model where you had a 3-tier architecture, where you had a web front end, you had a middle tier, and a back end database, it is very difficult for you to reason about the consistency as the failovers happen. And that's why we are recommending that you use actually the replicated store that we provide out of the box, where we take care of such things for you, and then you break down from 3-tier architecture to 2-tier architecture. The Reliable Services API that we didn't cover in this talk comes with Reliable Collection, which is Reliable Dictionary and Reliable Queue. You can create a local transaction. You can perform bunch of operation on those queues and those dictionary, and they're all consistent even when the failover happens. Yes?
Can you discuss patterns for approaching automated testing at the service and the application level? I'm particularly interested in integration testing between actors and how you deal with external resources or stubbing out external resources.
So if you have external resources, you can stub out them in your application. For the local testing, we recommend that you actually just run on a local dev cluster or the cluster in your lab and run on a real code with the chaos service. And so that way you will get the benefit of running on a real code. You can, so if the Reliable Services API, you can actually use frameworks like Unity and say, hey, I want to write my own iReliable state provider implementation. In this case, you want to write your own iState provider and the iCommunication provider for actor and stub those out. But those are not going to give you actually the real test. Like when you want to make sure that your service is going to run in production, you want to run with the real bits. This is one of the difference between the cloud service V1 as well as and this next gen cloud service, where in the cloud services V1 there was an emulator, and so if you run your test on emulator, there is no guarantee that it will actually run on a real production system. Here it's exact same bit. And we do all of our testing in the same way as well. We run on a real cluster, and then we run chaos. We have another version of chaos which actually that can do this on a much more faster pace. And so we are able to cover the system through a lot of transition in a small amount of time and find more failures.
Are you able to drive the service fabric from C#?
What do you define drive service fabric? Yes, yes. So the chaos service is actually using our C# API, which is called Testability API. There is a REST version of it, there is a C# version of it, there is a C version of it. So yes, the chaos service is just written as an application using public testability APIs that we provide. So you can run that in your harness. The testability comes with some pre-built scenario that you saw, which is, hey, I want to do a code package restart, I want to do a primary swap, or I want to basically take down a partition. You can define your own scenarios as well. So you can say, hey, this 4 sequence of step represents my test scenario, and I'm going to ask the testability subsystem, can you go run this scenario? Yes. So the question is there any other model of concurrency? So for the reliable actor API, the concurrency is turn-based because that's the definition of the actor programming model. If you are using the reliable services as well using reliable collection, the concurrency is basically multiple concurrency, and your isolation is defined by your transaction, your read-write transaction, which rows that you touch. And then if you are within the transaction, it's a repeatable read, and for enumeration, it's basically a snapshot-based isolation. Yes? So great question. We haven't talked about what you can actually put in your actor method. So for example, in the actor proxy, I made a call to say set value async. Now, if a failover are happening, that actor proxy is internally just going to keep retrying until it succeeds. Now, you may say, well, at some point in time, I want that guy to come out. Now, timeouts don't make sense because then you have no idea whether this timeout is going to work in this particular scenario, whereas some other scenarios, and these are random failures happening in the system. So we don't have a support for the cancellation token in the current framework. It will be added in the next few months where you can add a cancellation token in your actor interface method as well. And then you can cancel that at any point in time, and we will propagate that cancellation token from your proxy all the way to your actor implementation, and you will be able to cancel the calls. Yes? Right. So I'm not very familiar with the HPC, but the clustering technology, the failover clustering technology that is there in the Windows Server, we were part of that group at some point in time, and we decided to basically fork the code base because the failover clustering today has a lot of workloads running on top of them, and in order to move those workloads to this new cloud model, it was more important for us to actually make that switch. And so this can scale to a very large number of nodes. It was born from the cloud, going to cloud kind of paradigm versus that you want to do it with like 2 or 3 boxes. Yes. So the question is there a way for actor to basically pre-initialize itself or get warmed up, right? Yeah. So one of the ways you can do is to basically register a reminder, right? So you can register a reminder, and then even when a failover happens, the reminder will kick in. And in the reminder call, you can say, hey, I am already initialized. I'm not going to do anything. If it is not initialized, you will go and initialize a bunch of things. Yes? Actually, I can't hear you. Okay, so the question is that what happens if you change a state, and or what's the guidance for versioning your state when you're going from one version to another version? Well, the guideline remains the same. If you are writing any application that persists the state to a database, basically don't break the serialization protocol. So if, let's say, you were using data contract serializer, the data contract serializer has a very good guideline in terms of how do you version your data so that it's not broken. So you would not add any require fields, you would only add optional fields. You would do on deserialize or on serialize callbacks in order to initialize the stuff from another. You could also do something like, if you really have a breaking a schema change, you can stand up another application, migrate your data, and then say, hey, this is the application that I'm going to use. Yes? So the question is, do you have anything related to SignalR or reactive processing or reactive frameworks, right? Yeah, so the Actor framework does not have any integration today with Actor, with RX or any other reactor-based programming model. You can build one on top of it. No, we don't have that today. Oh, I actually, there is, so we didn't talk about one feature, which is actors do have a notification feature. The notifications are best effort, so you can use that notification feature to build some of the SignalR related scenarios that you may have. So you can define an interface which is basically iActor notification, and then from proxy you can register for the notification, and whenever the state changes, from within your actor, you can use that notification mechanism to notify your subscriber. We do the subscriber management for you. You don't have to resubscribe. Like if you have used Orleans will say, hey, you have to resubscribe every 30 seconds or one minute. You don't have to. The platform takes care of all of that for you. Thank you very much. Thank you for coming. Go have a party.